pleasure to see you all in Brazil. Only my friends get to this talk.
I have to record. I have to record.
I have a lot of friends, true. Been around a long time. So I'm going to wing through my talk. I'm going to talk right past a lot of details. But my talk will be posted in PowerPoint form on my website, so you can find it there. But the main thing I want to do is get across the argument that I'm going to make today. And the argument is all about this thing. We don't really have a name for it, but it's the business of connecting models with phenomena in nature. And I'm going to illustrate this with Fisher Lande type process models and with sexual radiations illustrated with birds of paradise. But the problem is general of connecting models to reality. And there's psychology here and so forth, but I want to focus on the things that we can solve. Here we go. Shouldn't screw that. All right, so here's my argument. FLP, Fisher Lande process. These models have been used to look at the logical consequences of sexual selection, but they're almost never tested in the real world. And that's true of a lot of models that we construct. So I'm going to show the phenotypic tango, we call it, which is a more general version of the model presented by Lande. I'll show you that in a minute. I'm going to point out that we can't evaluate its predictions analytically, but we can do computer simulations. And we can test whether the phenotypic tango can account for sexual radiations. I'm going to show you one test today. And the conclusion is, yes, it can, but we're going to have to tweak the models that we've been using to make them to account for reality. I'm also going to use two other kinds of models, Brownian motion and Ornstein-Uhlenbeck processes. These are generic models, and I'm going to show you that they too can account for the radiation. And I'm going to focus mainly on the point that it takes a little bit of tweaking again to make these two kinds of models talk to each other. And the way to do that is to standardize the data so that the results of this model are in the same units as the results of this model. And then I'm going to make some conclusions, and we'll talk briefly about the future, and we'll thank several people in the room for their help. Okay, so for those of you who've never encountered the Fisher Lande process, it's due to Fisher, publications 1915, 1930, 1958. And he's most known for this concept of the runaway, in which the traits in males, we're going to refer to them as ornaments. Of course, they're really not. That's just a shorthand. These extravagant sexually dimorphic characters in males run away with preferences, Fisher proposed. Oops. So here's Lande, who made an actual model of the things that Fisher was talking about. And he assumed that the traits were normally distributed, the ornament, which I'm showing here in blue, and the preferences for that ornament in the females were normally distributed within a population, standard Lande, and they were both polygenic traits, affected by many genes. So here are the ingredients, and the basic idea is that the ornament in the male affects his survival. Females prefer exert sexual preferences for that ornament. And that female mating preference based on the ornament does not affect her survival or her fecundity. We're going to relax that. Both traits are heritable, as I said, polygenic, and because of assortative mating and sexual selection, the traits end up being genetically correlated within populations, and that genetic correlation is maintained in a selection mutation drift balance. Okay, so here's the basic idea. Here's what Fisher was talking. These are results from Lande, that there would be a neutral line of equilibrium. Populations would zoom off, getting more elaborate ornaments and preferences, or losing them to minus infinity in the other direction. Now this runaway result requires somewhat drastic genetic assumptions. Do you agree, Derek?
Recontrol.
Yes. So a more conservative version, I think we agree on this point, is this walk towards equilibrium. And this is the one that I'm going to be talking about today in the models. And the idea from Lande is that this could happen less probable than this model, in which populations tend to evolve towards a neutral line of equilibria. And most populations spend their time drifting up and down this line. And they drift up and down the line because there's only selection on the male trait. There's no selection on the preferences. All right. We're we're going to introduce not only natural selection on the male trait, but also selection on the preferences. And if we had a single trait, it would look like this. There's this rubber band like Ornstein-Uhlenbeck process. There's a convex selection function of fitness as a function of the ornament, and the rubber band, that process pulls the population back towards the optimum, and we have another rubber band in the other direction. I've only shown one that would pull it in this direction. And here we see a population that's experiencing, that could be held in a balance between natural selection pulling it towards the optimum and some other force, sexual selection. And a general property of the Fisher Lande process is that ornaments can equilibrate at some distance from their optimum because of this dynamic balance between the two forces. In the case of female preference, however, we're going to imagine that there's only this force of natural selection, similar kind of process, but ornaments will tend to equilibrate right under the optimum, under natural selection. Yeah, that's the basic idea. Okay, so now, why not go out in the world and test these models with the biggest form of data, which would be sexual radiations, that is, sexual selection, radiations driven by sexual selection. And the problem is that the models are hardly ever connected up with the phenomenon of sexual radiation in nature. And we're going to focus on how we can break that impasse. The simple way we're going to break it is find data that enables the model to talk to nature, and also to tweak the models so that they fit the phenomenology that we're encountering out there in nature. So we've got to have crosstalk in both directions. We're going to have two classes of models, and we need to have the models talk with each other as well. Okay, so the solution is to get data, and we're going to use what's been called the iconic example of sexual radiation birds of paradise. They have several attributes that are useful to us. There's a time-calibrated phylogeny, so that gives us times of divergence between pairs of taxa. It's clear that there are male displays and female choice based on those displays. It fits the properties of the Lande-Fisher framework. There's a big morphological component to the male display. That's not all that's going on, but it's there. And we have data on male morphology. We're going to talk about the other kinds of data that we'd like as well. Okay, so birds of paradise are not only cool, but we can connect them up with our models. Here's a phylogeny published by Ersted in 2009. It's time calibrated. You can see the estimated age of the root of the bird of paradise, part of the bird of paradise clade is about 23, 24 million years ago. That's a long time, longer than they were expecting. So it's not like we have to have all the bird of paradise radiation evolve overnight. We've got 23 million years for this to play out. And so the actual problem when we're fitting the models is actually put constraints in the model so that we don't blow up, even with the walk towards version of the Fisher Lande process. Okay, so we're going to use this actual phylogeny in our data analysis, and we're going to focus on the part of the tree where we've actually got morphological data, and that's going to be a single genus, 14 populations, paradisia. I'll show you those in a minute. They look like this. That's why we're using it as our icon. But here are all these crazy things that are happening in birds of paradise. Extraordinary morphology is apparent in this slide. Okay, if we look at paradisia, this shows one of the displays. And there's a huge, huge store of observations and especially video compiled by Scholes and Lamont at the Cornell Laboratory of Ornithology. Fabulous online resource. And if you look at those videos and read the descriptions in the primary literature, you find out that males, here are two males, commonly adopt postures, and these postures represent modules of display. The displays are very complicated. There's a posture in which the males form a static shape using the plumage of, here you can see both the tails and the wings of each of the plumes on the back. In addition to the morphological and coloration aspects of the display, in the module also is choreography. There's movement during this pattern. I've got 5 minutes left. Okay, so anyway, it's modular and complicated. Okay, let's look at the phenotypic tango. Our model is going to be bivariate, and so we're going to represent the preference bivariate mean and the display by the ornament bivariate mean with dots And I'm going to show you circles around those dots, which represent our model for the equilibrium, 95% confidence limits, stripping away sexual selection. And I'm going to show the tango as a male population ornament mean connected to a female preference mean in bivariate space connected by a line. Okay, so here's the good news. The model, this bivariate model, is at least multivariate. It's more general than other ones, but it's so complicated enough that we don't yet have an analytical solution, but we can do simulations to figure out its behavior. So here's 100 populations evolving under the process, just focusing on the males, and I've stripped away sexual selection, so this is natural selection only. At equilibrium, we have 100 population means dancing about this little blue circle that you can't see. That's the equilibrium. Here are the 100, here's an example of 100 female preference means dancing about their natural selection optimum. If we add sexual selection to the model, now pairs of populations dance, the means dance, and you can see that the preferences are drawn outside of their natural selection 95% confidence limits, but more spectacularly, the male ornament means are drawn out. And they can dance far away from their natural selection optimum. If we reverse the process so that there's weak selection on the ornaments and strong selection on the preferences, we get pretty much this picture here. Now the preferences, so the upshot of this is the preferences are totally dominating the dynamics of the system. And a useful fact we get out of the animations is that we can approximate the equilibrium of ornaments under the complete process just by knowing the equilibrium properties of the ornaments of the preferences under natural selection. So that's going to be useful to us. Okay, I'm not going to show you the animations, but you can go to my website and see them there. Go to chapter 12. phenotypicevolution.com. No spaces. All right. So let's try fitting the data with a tango model. I'll show you this quickly. Here's the bird of paradise genus that we're going to focus on, 7 species. Here are data from Mary LaCroix. These are the only data that I could find in the literature without doing field work myself. And I'm plotting male tail length and male wing length, and I've standardized everything so we're in unison within population phenotypic standard deviations. So here's the female characters, here are the male characters. If we wanted to account for an ellipse like this in the evolution of an ornament, what do we have to do to the Fisher Lande process? Well, we have to build in correlation in the selection surface, in the preferences that are acting on the trait. And if we do that, we'll produce a dancing set of preferences connected to ornaments, and we can produce a cloud very much like what Mary observed. So that's a crucial element that we need to add to the data. But the point is, we can't account for the bivariate patterns in morphological or ornament data in general. We can also account for the amount of diversification. If you look back to that slide, we've got about plus or minus 12 phenotypic standard deviations in both traits. If we just focus on a single trait, we can get that amount of evolution in 100,000 generations rather easily. But we have to do an absurd thing. We have to assume that preferences are under extraordinarily weak selection. The other thing we could do is assume that the preferences are affected by natural selection optima that move. And that's what we're going to explore next. We did that with the Ornstein-Uhlenbeck processes, which have good properties and bad. One of the bad things is that they're univariate, not multivariate, but we have analytical solutions, and we can get likelihood solutions to our fits. Let me just show you what they look like. Brownian motion, I'm done. It's a good thing I gave you my punchline right at the start.